Okay, hello everyone. I'm Sohee Park from Yonsei University in South Korea. It is a great pleasure to participate in this great session. And thank you, Dr. Dong-Yoon Kim, for having us here. So we're going to have four speakers today. So we will start out with Dr. Myunghee Cho from Department of Statistics at Seoul National University in South Korea. She's going to give a presentation on sequential decision-making with uncertainty, contextual bandits as a missing data problem. Dr. Cho, it's all yours.
Oh, thank you. I really appreciate Professor Park for introduction, and sincerely thank Professor Seungyeoun Lee for invitation. And it's my great honor and delight to meet all of you for International Day of Women in Statistics and Data Science. So my topic today is contextual bandit. You may or may not heard of contextual bandit, but we are all familiar with these company names. And these companies use contextual bandit algorithm for personal recommendations. And they are e-commerce companies, and there is a common structure. And these e-companies interact with users through digital devices such as web page or mobile app, and they display items and users click a displayed item if they like, but they cannot display all the items because there are so many, and they have to make decisions which items to display through the web device. And a simplified version of this problem can be formulated through multi-arm bandit. Originally, multi-arm bandit is illustrated by pulling arms of slot machines. So if you go to casino place and you have to make decision which slot machine to play. So let's say you go to arm 1 and pull it and receive the reward, and maybe you go to arm 4 and play the machine and receive the reward. And why do we hop around different machines? To find a good one to give better rewards. So based on your experience, you make a decision which arm to play. And the goal of multi-arm bandit is to find a strategy that will give the player the most cumulative rewards. So for argument's sake, suppose that the reward from arm I at round T is independently identically distributed with mean mu sub I. And if you know mu sub i's, then the decision making is easy. You just pick the machine with the largest mu sub I. However, we do not know them, so we have to make decision without fully knowing mu sub i's. So to wit, multi-arm bandit is a sequential decision-making problem with uncertainty. It is decision-making problem because we have to make decision which arm to play or which items to display. It is sequential because we have to make decision repeatedly over time or over round. And you have to do this with all uncertainty. So without knowing mu sub i's or without knowing the customer's preference. So what I'm going to cover today is an extension of this multi-arm bandit called contextual bandit. So context here, the context represent features of users and items, and that allow personalized recommendations. So in making decisions with uncertainty, there are two potentially conflicting tasks. We have to maximize reward. That's called exploitation. To do that, we have to select the arm with highest predicted click rate. And also we have to reduce uncertainty via learning. That's called exploration. To do that, we have to select the arm that estimate the unknown parameter more efficiently. And that may not help maximizing rewards. And the contextual bandit belongs to reinforcement learning, in that we interact with environment because we select the arm, and then the environment give the reward for our selected machine. And in a way, we can choose what to observe, while in supervised or unsupervised learning, data are given as a whole in a passive way. There are many applications, and I would like to go over how the contextual bandit could work in mobile health app to enhance physical activities. So the mHealth system has various types of messages to be sent at specific times of day. So arms are the messages, and the context are the features of the message. And then system selects one type and push the message to the app user. And then user reacts to the message and give feedback, in this case made by a step count. And based on this user feedback, the system updates its message selecting strategy. For the remainder of the talk, I will review two popular existing contextual bandit called upper confidence bound, lean UCB, and Thompson sampling, lean TS. And then I will cast the contextual bandit as a missing data problem, and then propose a new method, doubly robust Thompson sampling. And there are two new methods, but high ran, but because of time, I will just briefly cover that. So let me first introduce the notation. So let x of I of t be d-dimensional context from for arm I, where I goes to 1 to n at round t. And we are given context information for all arms, x of 1 to x of n. And each round, the agent chooses an arm, A of t, that's the arm index for the arm index for the chosen arm. And we assume that the reward for arm I, y sub it, is xi beta plus eta I, and beta unknown parameters, and eta is a sigma sub Gaussian random variable with mean 0 given history h of t, which include all the data up to round t-1 and the context information at round t. And we also assume that the two norm of x and beta are bounded. And each round, an agent received the reward y sub a of t. And maybe it's obvious, but we do not observe y sub I if I, the ith arm, is not the selected one. So we don't get the reward for the slot machine that we did not pull. And the goal of the contextual bandit is to maximize the expected cumulative reward. And optimal arm, denoted by A star of t, is the arm index whose reward is the maximum. And the optimal arm can change over t. And then instantaneous regret, denoted by regret of t, is the difference between the expected reward for the optimal arm and the selected arm. And this is the loss or the penalty incurred by choosing non-optimal arm, by choosing a wrong arm. And the cumulative regret is the sum over the instantaneous regret over all rounds. And this cumulative regret usually is used as a evaluation tool for an algorithm. And we want that to be sublinear in t. Because if it's linear in t, that means we don't learn what optimal arm is over the round. So there are two popular existing algorithm, Lin UCB and Lin TS, Thompson sampling. Okay. So Lin UCB, first is Lin UCB. Algorithm selects the arm with the highest UCB score, where the score is X beta hat plus some uncertainty terms. That's a multiple of standard deviation like term, where beta hat is the ridge estimator based on the selected arm up to round t-1. And this Lin UCB naturally blends between exploitation and exploration, because we end up selecting if the first term is high, which is promotes exploitation, and or uncertainty is high, which promote exploration. So Abashi Corey showed that with high probability, this Lin UCB has regret upper bound that is sublinear in t square root of t and linear in d square root of t. The another popular algorithm is Thompson sampling, Lin TS, and Thompson sampling is a variant of UCB and incorporates uncertainty of the estimator by randomly drawing from a posterior distribution. So beta tilde is drawn from a normal distribution with mean beta hat, that's the ridge estimator. Then we select the arm greedily, meaning that we select the arm whose expected, the predicted reward is the highest based on beta tilde. And Agrol and Goyle showed with high probability that the cumulative regret can be bounded by square root of t. But in terms of d, that would be d square root of d. So there is extra square root of d in the bound that is incurred from randomly choosing sampling beta tilde. However, Thompson sampling is very popular due to its simple implementation and it's good empirical performance. So let me go over a bit of key steps, key idea of bounding this cumulative regret for Lin UCB. So regret is incurred by choosing a wrong arm. And why do we choose a wrong arm? Because we don't know the parameter value. So the regret is typically related to the estimation error. So suppose that with high probability, we can bound the prediction error by, let's say, B, then we can show that instantaneous regret can be bounded in terms of this prediction error bounded B. So the bounding this estimation error is the key. However, the bounding the error is not straightforward in bandit setting. If the arm I is selected randomly, then the estimation error can be expressed as a sum of mean zero independent random variables, where A star is the gram matrix and E star is the error. But for bandit setting, the estimation error can be expressed but in a similar form, but the gram matrix is a function of arm selection indicator, A of tau. And this A of tau depends on the data from the previous rounds. So there is no independence between the gram matrix and the error term. The same technique cannot be utilized. So to solve the problem, so De La Peña et al. Bound the self-normalized norm, that's the norm weighted by the gram matrix using conditional independence and the martingale inequality. And Abashi and Corey finally used multiplicative decomposition of the prediction error through Cauchy-Schwarz inequality, and expressed the bound in two terms, two multiplicative terms. And the second term can be bounded by using the Dulapeñas result. And each term contribute square root d for the error bound. So as long as we use the multiplicative decomposition, the error bound d cannot be smaller, seems like. And most existing regret analysis of various contextual bandits rely on this technique. However, some additive regret decompositions are possible. So if we let D sub j be the instantaneous regret incurred by arm j, then for any estimator, this D sub j can be bounded by two additive terms, where the first term is the 2 norm of the estimator. However, we can capitalize on this structure because 2 norm bound for the rich estimator cannot be obtained. So the question arises whether we can find an estimator where whose 2 norm can be bounded, and therefore we can capitalize on this additive regret decomposition to avoid a compounding of the error term. So to answer this question, by answering this question, we propose a doubly robust Thompson sampling. So to start, I will give a fresh perspective on contextual bandit problems. So in bandit problems, in bandit setting, we have completely observed the context X's and partially observed the rewards Y's, because the reward is observed only for the selected arm. Okay, and the rich estimator for lin UCB or lin TS utilizes only the context and reward pair of the selected arm shown in gray cells. So this structure resembles missing data setup when the arm selection indicator is taken as an observation indicator. But there are differences, but let me just skip this one at this moment. And let's just step aside a little bit and go over the approaches, what approaches for handling missing data. Okay, there are two main approaches to handle missing data. First is imputation approach, where you replace missing quantities with its conditional expectation given observed data using imputation model. And another one is inverse probability weighting, IPW, that uses only the completely observed record, but weigh each record by the inverse of the probability of observation. And each approach requires auxiliary models. So imputation approach, imputation model, inverse probability weighting, inverse probability of observation model. And the consistency of the estimator requires that these auxiliary models are correctly specified. And a doubly robust method is a combination of imputation and IPW method. So it requires both auxiliary models. But the consistency of the estimator of DR method relies on the correct specification of either of the auxiliary models, not both. So that's where the name doubly robust comes from. And in contextual bandit problem, the probability of observation for the reward is known, and it's we control that, so the consistency of the method is guaranteed. So to describe the doubly robust method, we first denote pi sub I by pi sub I, the probability of selecting arm I at round T. And then we define the pseudo reward as a combination of two quantities. The predicted value from imputation model and the observed reward. And it turns out the conditional expectation of this pseudo reward is x beta. So the pseudo reward is the unbiased predictor of the of y. And the DR estimator can be defined as the rich estimator using all context from all arms selected and not selected, and the pseudo reward. Okay. And now you can see that the gram matrix of the DR estimator does not depend on the index of arm index, the index of arm selection. So eventually we can use independence argument and the related techniques. And the DR Thompson sampling uses this DR estimator instead of rich estimator, and inherit the structure of Thompson sampling. So I'm not going to go over details, and I'm going to just skip. So at the end, we can bound the two norm of this DR estimator. And using that, we can bound the regret of the DR Thompson cumulative regret, upper bound of the cumulative regret as a square root t, and it's function of 1 over phi square. And this phi square is the minimum eigenvalue of the covariance of matrix of the context vectors. And in many practical cases, 1 over phi square is order d. So eventually we get regret bound of d square root of t, which is square root d sharper than ln TS, the original Thompson sampling. Okay, so we're going, so it numerical studies shows well the good performance of the RTS. And then maybe the next question is whether we can shave extra square root t from other algorithms such as ln UCB by applying a similar technique. But answer is no. In DRTS, we inherited main structure of ln Thompson sampling algorithm, replacing rich estimator with the DR estimator. But we could do this because arm selection is random. Okay. However, in ln UCB, the arm selection is deterministic. So we cannot apply missing data technique. So what can we do if the arm selection is not random? Arm selection is deterministic. So to solve the problem, we propose hybridization by randomization, high-ran algorithm. And so if the arm selection is not random, then we generate external random device H sub t and randomly draw from 1 to n with a known non-zero probability. And we can construct the pseudo reward in a similar way. But the problem is if the arm selection indicator is different from the externally generated random value, then the reward is not available. So we can't compute this pseudo value. So we propose this hybrid form. So this hybrid estimator is just it's as the name says, it's hybrid. If everything is observed, if reward is observed, use all data, and if it's not observed, use the selected arm data from selected arm. I'm sorry, data from selected arm. And using this hybrid estimator, we can design an algorithm. And it turns out that this estimator has a square root of dt regret bound. Okay, so as a summary, I'm sorry that I have to rush to fit in 25 minutes, but contextual bandit algorithm help sequential decision making with uncertainty, useful for many applications. So we introduced DRTS and higher-end new algorithm, viewing the bandit problem as a missing data problem in employing all context. And therefore, we could shave the upper bound by square root d. And Won-young Kim, Jisoo Kim, and Min-han Oh are my proud collaborators, and thank you.
Thank you very much for great presentation, Dr. Myunghee Paik. Yeah, there are a lot of clapping going on the window.
Thank you.
So, yeah, since we are on the schedule, just right on the schedule. So I guess we will have to move on to the second speaker. But I forgot to mention that this session was actually organized by Korean Statistical Society's Women in Statistics. So we have the committee for Korean women statistics. So the fourth speaker, Dr. Seungyeoun Lee, is going to also introduce briefly about that as well. So we will move on to the second speaker. Second speaker, unfortunately, she had the class to teach, so she recorded her presentation, and we'll play that video clip for you. Okay, thank you. Dr. Lee, I think you should unmute your microphone when you're playing the video clip.
Or PhD
There we go.
doctors
Thank
from
you.
universities, because we deal with some several epidemiological Department of Statistics, Kyungpook National University in Korea. So I'm very honored to have my research presentation in International Day of Women in Statistics and Data Science. So my research title is Modeling and Data Analysis of COVID-19 Transmission Dynamics in Korea. So I will give some introduction of mathematical or statistical modeling. So there are three main objectives to do those research. First, we would like to provide much insight into dynamics of infectious disease. To do so, we estimate or predict the course of an outbreak. And then, second, we evaluate control strategies to control an epidemic. And then sometimes we predict how many cases are reported like that. We just call those research part as forecasting. So as time goes by, our important research question has been changed like that. So I will introduce my collaborators. Like I'm working with experts from public health or National Institute, and sometimes I'm working with some professors or PhD doctors from universities, because we deal with some several epidemiological data. So for some reasons, and I'm working with some experts from very different research fields. So here I will introduce main three research topics which I studied for last 2 years. And then first topic is about estimation of COVID-19 transmission dynamics. Yeah. So before the vaccination has been started in February 2021 in Korea, so our focusing was how to manage those transmission dynamics by using non-pharmaceutical interventions such as social distancing and wearing masks and so on. So in that period, so our government has implemented the different level of social distancing in different geographical areas in Korea. So our question was, which level is most effective according to the different area? So we incorporated the levels of social distancing implemented in Korea, and also we considered several important control interventions and important events. So here, this graph shows some timeline, and including the level of social distancing, like this square box indicates the level of social distancing implemented in Korea, like level 2 or level 2.5 and so on. So we considered those some time points as some parameters, time-dependent parameters into our model. Yeah, so this graph shows some outline. So we used two different models. First one is compartment model. So SEIHR is compartment model. And also the second model is a statistical model, which is called as renewal equation. So by using these two models, we successfully forecast how many cases are reported according to the different intensity of control interventions. For example, if the government maintain the intermediate level of social distancing, then how many cases are forecasted like that? So different like intensities, like low level or intermediate level and high level. So, and then we can forecast the numbers by 7 geographical areas in Korea. In that some forecasting part, we use the distribution, like probability distribution of reproduction numbers. Like reproduction number is very important threshold, which means that how many secondary cases are reported with from the primary case, like that. So we first of all estimate the probability distribution from the previous data points. And then this research topic has been published in this paper. So I will give some details, some explanations about the methodology. So step 1, we construct a mathematical model like SEIHR compartment model, and then we estimate unknown parameters. Here, unknown parameters are time-dependent transmission rates. And then we can derive the effective reproduction number from the estimated time-dependent parameters data. So as you can see, so these dot points represents the observed data, like COVID-19 confirmed cases. And the solid line shows the estimated values of COVID-19 cases here. So, yeah. So similarly, we estimate the 7 geographical area data like this. So as you can see, our fitted model can capture very well like the observed cases. And then we consider some delay effect, because if government implement the different level of social distancing, the effect has been obviously revealed after maybe 2 weeks or 1 week. So there might have some delay. So we considered those delay effect. So by using some correlation study, we can conclude that there are some more than 7 days delay in Korea. Here, so we incorporated those delay effect into our probability distribution of effective reproduction numbers. So depending on the different intensity, like low level social distancing and intermediate social distancing, high level social distancing, then we calculate the different probability distributions like that. So as time, and then finally, we forecast the number of cases, and then to measure or to validate accuracy, we employed MAPE to compare the observed cases and forecasted cases. Yeah, and then in this table, so our MAPE shows the like 11.11 or 13 and 20, depending on different areas. So we can interpret that like we can get some good forecasting from our suggested method. So next topic is about analysis of the vaccination strategies. So as time goes by, vaccination has been implemented, and also so government implemented not only non-pharmaceutical intervention, but also pharmaceutical intervention together. So here our question is, which age group should be prioritized, or how many doses should be prepared for vaccination? So to answer those questions, we construct some research questions, and we did several studies. So this study is kind of ongoing study, so I will briefly explain what we are doing now. And here, if you look at the cumulative cases, like this, like Seoul and Gyeonggi and Incheon shows some high proportion of COVID-19 cases, like more than 40%. But compared to the COVID-19 cases, let's look at the right figure here. So this shows the unreported rate. So as you can see, that Daegu and Kyungpook. So in this, some area has much more higher proportion than other regions. So it means that, so depending on the regions, they have different proportion, some distribution, like based on cumulative cases and on reported rate. So we consider those some points. We construct the new model here. So this is our working outline. The first part, like we construct the age structured model. So an age structured model has some strong point, because this model can capture some heterogeneous transmission dynamics between age groups. So to explain this property, we employed content metrics in our model. And then we estimate the transmission dynamics by age groups. And depending on the seropositivity and on the reported rate, so we can forecast number of cases as we did before in the first research topic. But it can be some extended work expanded work. And then finally, we can analyze how many vaccines should be prepared, which age group should be prioritized. By analyzing several scenarios, we can have some results, like we can conclude which what kind of strategies should be prepared. So this model is our age-structured model. So here, basically, we also use SEIHR compartment model, but it is expanded to the vaccination part here. And then we consider the death cases as well. This I represents the specific age groups. So this equation is ordinary difference equations, and this table shows the summary of parameters which we used. And then that contact matrix. So here, the contact matrix element MIJ is the mean number of contacts between age groups, and these components of contact matrix is contact matrix consists of four different contact matrices, sub-contact matrices, like contact matrices at home and at work, at school, at some community or others. So, but here in our study, we only use the total contact matrix M, which is the sum of elements from the sub-contact matrices. So this graph shows some results. Maybe I will check the time. Yeah, okay. And then we can get some good estimation, like total and depending on different age groups. And also, as time goes by, vaccination has been changed like that here. So this is the results. So by using the limited different doses like this, we estimate the number of cases. And then if we use 300,000 doses, then we can successfully control the epidemic here. And also we changed our priority age group and the scheduling based on scenario 1, scenario 2, and scenario 3. And we also get some comparisons. And not only using cases, but also using deaths, we can have different effective strategies here. So lastly, I will introduce some new outbreak detection using machine learning methods. Here, so as time goes by, we experienced several waves, such as new outbreak, first wave, and second wave, and third wave. After that, the new variant has been occurred, and then we have some new outbreak like fourth wave and fifth wave, and so on. So based on only data, we would like to estimate the start time of new outbreak. Here, by using some machine learning classification method from SVM and random forest and XGBoost, we have 3 different transmission patterns, such as increase, maintain, decrease. We made those labels, and then we give specific standard to detect the start point of new outbreak. So firstly, we generate the sample data, like we use the dose period, and so main idea is we chop the data like 21 days, 21 days, 21 days. We chop the data and then slide the time window by 1 day and 1 day, 1 day. In this way, we made a sample data like about 1,000 number of samples. And then to make some labels like increase, maintain, decrease, we need some function of risk index. So we newly defined function of risk index to capture the change of transmission dynamics. So by using some regression analysis, we made some risk index like this. And then by each sample, we can calculate the risk index value. So it means that each sample data has one risk index value. And then, so we divide 3 parts, like some, you can just guess, like we can just sample the values from the uniform distribution. So we just regularly divided 3 parts as level 1, level 2, level 3. Like we labeled decrease, maintain, increase according to the values of risk index. And then, so we did some classification by using machine learning methods. So we can get the accuracy about more than 90%. So we can conclude that our methods to capture the transmission dynamics works very well. So and then we go for next step. Okay, next step. So we employed this new method into our observed data. So this A shows the observed data, and this vertical line shows the first start time of new outbreak. And then this B shows our some results. So this star shows the start time of new outbreak estimated by risk index. So as you can see, the observed time and estimated times are well matched. And then, so by using different machine learning methods like random forest and SVM and XGBoost, we can get the similar results between the observed time points and estimated time points. So for each outbreak, like first outbreak and second outbreak and 7 last outbreak, we compared our results with observed time points. And then we also can get our methods can work very well, like, yeah. Okay. And then I just introduced the main 3 research topics here. And then, so research results are introduced in many times in broadcast, like. So these are references which I published several papers about the modeling of COVID-19 in Korea. Yeah, thank you very much.
Okay, thank you, Dr. Hyojung Lee. So there are a lot of clapping going on again. I will certainly transfer that clapping to Dr. Lee later. Okay, I think we are back on time very well. So let me introduce the third speaker. She is Dr. Min Jin Ha from Yonsei University, same university as me, from Korea. And she's going to give a presentation on Bayesian robust learning in graphical models. Dr. Ha, please.
Yeah. Can you see my screen?
Yes, we can.
Okay. Maybe I don't see the screen. So let me.
Now the screen is not full.
Right. Let me. Oh, okay. So is it full now?
Yes, but it's a little bit small. But I think it's okay. Can you make it a little bigger?
So if I share the PDF, be better. Is it better?
I think it's okay. Yeah.
Okay. Okay, so we don't have much time for actually managing my screen, so I will start. So thank you for the invitation. So this is a great opportunity to get together as a woman statistician and a data scientist. So and also it is a great opportunity to hear like very interesting talks here in this session. Okay. So today I will present about my recent work on robust framework in graphical models. So this is ongoing work. I'm like doing some hopefully final revision on this work. So hopefully it will be coming out soon. So this work is joint work with my postdoc at when I was in MD Anderson, Munita Chakraborty. She's in UT Medical branch now. She's and Veera Balladande Yusapani at Michigan University, and Anindya Badra from Purdue University. Okay. So the data structure that I'm considering is actually multi-level data. So for the same set of samples, we actually obtain different layers of the data, and then the data has some kind of order. It can have some order. So in genomics, the example is like a multi-platform data, like at DNA level, like gene expression, protein expression data, even metabolome and the microbiome data are obtained. Very, very high dimensional data are obtained. High dimensional multi-level data are like available in the field. So and in this with this data sets, I would like to model the dependencies between the features. So to do it, so maybe we can consider network modeling, like using graphical models. So the most widely used approach is undirected graph that allows only undirected edges between the features. And the directed graph is like used to represent causal relations between the random variables. However, when we have only observational data, it's not all the edges are not identifiable. And then the chain graph is the actually the mixture of the undirected graph and the directed graph. So actually, chain graph is a kind of general graph that include both directed and undirected graphs. So, and also using this kind of graphical modeling, we can actually consider in more complicated situations, like when there is latent or known group structure within the samples. And also we can, using this group structure, we can kind of construct the differential networks to compare the networks between the groups. And also beyond the EDA, beyond using the graphical models as a EDA technique, we can actually use the network for modeling the prognostic models. So in this case, we actually still need to handle high dimensionality. Even one platform provides a lot of features, like 10,000, right? And also we need to, if the model permits, we can kind of incorporate multiple the ordered layers. So sometimes if you want to consider the order, and you can we can actually consider to model this kind of order. And also right, and yeah, so these are the main challenges to handle the modeling the dependencies. So okay, so the chain graph structure, so the graphical structure that I'm considering here is called chain graph structure. That includes both the undirected edges and directed edges. So the in the layer 1, it has the topmost layer includes the DNA, for example, and then the second layer includes the gene expression, third protein expression, and the last layer outcome. So because if we can actually assume the order of the layers between the layers. We can actually, however, within the layer, we don't have order between the random variables. So within the layer, we allow only undirected edges, and between layers, utilizing the order between the layers, we can model the directed edges between the layers. So our objective here is to understand the conditional dependencies while accounting for the order among multiple layers. So if we actually, a chain graph structure, chain graph model has some Markov property. The Markov property is relevant to the conditional dependencies. So by actually constructing the chain graph model, we can interpret the edges with the conditional dependencies. Okay, so this is the mathematical setup for what I am doing. G is the chain graph with the a set of node 1 to P. The whole features across the layers are like denoted by the node set V, and then the edge set E includes both directed and undirected edges between the variables. So we assume in priori that a partitioning T, so the whole random variables 1 to P is partitioned into Q layers. Okay, so we already know the layer membership, and also we know the order between the layers in priori. So if the partitioning has the order, then it is called dependence chain. So what it means is that one variable in layer 1 can affect variables in layer 2 to layer Q. So a variable in layer 2 can affect variables in layer 3 to layer Q. However, not in the opposite direction. So the directions between the layers can go only forward, not to backward. Okay. So this is the dependence chain. So chain graph is once we have the chain graph, unfortunately for different from the directed graph and the directed or cyclic graph and the undirected graph, chain graph has multiple Markov properties that we can consider. However, in this work, I'm going to use Anderson's Markov property. So the Markov property, if we have no edge between random variable u and v, then it means the corresponding random variables yu and yv is conditionally independent, given the C is actually the cumulative set, Q if it is QL. So it is the cumulative of the union of all the random variables in the preceding layers up to the current layer L. Okay. So the cumulative of the WISK layer, right? The layer that includes the node V. The random variable yu and yv is conditionally independent given all the other variables in the cumulative of v. Okay, and then if it has the undirected edges between two different layers, then it means they are conditionally independent given the cumulatives up to the TV minus 1 layer. So the previous layer of the WISK layer. Okay. So depending on it is the directed edge or undirected edge, the conditioning set is different. Okay. So this conditioning set is called Anderson's AMP conditioning set. Okay. So then we can actually in the Anderson proved that if we use the SEM-like block regression model, the zero structure of the mean parameter here and the precision parameter here can the implying conditional independencies of the mean parameter and the precision parameter we can actually identify these kind of conditional independencies implied by the A and P. So it means that the graph and the statistical model here is kind of faithful, so that we can identify the A and P macro property from this model. Okay, so I will briefly explain the Gaussian chain graph model here. So it should assume normality here. So Y is following a big multivariate normal distribution with a precision matrix omega. And omega incorporates some conditional independent structure, and omega is decomposed into the mean part B, and the precision part K. And the mean parameter is actually encode the directed edges between layer. So if the zero element of B is equivalent to there is no edge between U to V. Okay, and then after actually adjusting for the effect from the directed edges, the residual part is still following normal distribution with the non-diagonal matrix. There is some elements in the off-diagonal part of K with the precision matrix K. And then the zero structure of K actually encodes the undirected edges between the nodes V and U. Okay. Using the Gaussian distribution property, we can actually nicely decompose the full joint model into component-wise or layer-wise block regressions here. So our working model here can be like a block recursive normal regressions with undirected Gaussian graph. So what it means is that for the first layer, we don't need to we don't have any preceding layer, right? So we can just run the undirected graph by finding the zero structure in the precision matrix K. And then from the second layer to the last layer, we can learn the B structure, zero structure of B, the mean parameter, and then the zero structure of the K, of the which is the precision parameter. And then actually the Y tau K is the multivariate response, and then this multivariate response is regressed on all the preceding variables. So we can actually the whole of the big joint big problem boils down to a multiple smaller block regressions here. So this work has been done from 2006, Darton and Isler. So this paper only handles low dimensional case, and then a long time later, Lin is using the lasso penalty on the K, the precision parameter K and the B. They actually solve the block regression to actually get the chain graph. And then this is my paper, so 2021. This paper handles this regression using neighborhood selection with Bayesian variable selection. Okay. So it has been the work has been done for both Bayesian and frequentist framework. However, the next question is these methods, all of these methods are like heavily relied on the Gaussian assumptions on the multivariate data. So our question is that do our data follow normal distribution really? So we actually try to check each of the gene, for example, copy number aberration MAPK1 gene. So it's like a great normal like bell shape. However, if we see the tail part here, if you see the QQ plot, you can see that there is perfect tail, right? And then the H score is like a p-value, the transformed p-value from the Kolmogorov-Smirnov test with the normal distribution. So H-score, the bigger H-score means more deviated from the normal distribution. So if we check this one, like by the platforms, there is different distribution, like it's very, very different. And also for the node specific, if we see each random variable, the behavior of the non-normality is very different, right? So they are very, very spreaded. The H-score is very spreaded. So this observation is kind of motivation for our work. So our work is that we cannot handle all kinds of situations. However, our setting, our scenario that we want to handle is that it's still limited, but little robust than the Gaussian assumption. So we are assuming that the marginal distributions are heavy-tailed, so that the joint multivariate distribution is no longer Gaussian. Okay? So like if we don't think about robust procedure when we actually construct the Gaussian graphical model, when we construct the chain graph, if we just blindly use Gaussian chain graph model approaches, so this approach can result in incorrect inference on the network structure. And then the second is the zero structures in the mean and the Prism parameters identified by the blood regressions that I just showed is no longer, the edges are no longer satisfy the AMP, Anderson's AMP Markov property. So we cannot tell it as the conditional independencies anymore. Okay. So by modeling in our framework, by modeling the marginal non-normal behaviors of nodes, we resolve the issues in a new framework of robust chain graph models. So our goal is so we have two goals. So first, we want to do the accurate network structure identification. And then second is that we want to do some theoretical work for interpretable notions of independencies on the original scale. So actually, the robust procedure, like such as using like multivariate T distribution, it has been already developed in other groups. However, most of those methods, the interpretation, the conditional independence interpretation is only on the transformed variable, not on the original scale of the variable. So, therefore, we just wanna interpret the network structure based on the original scale of the random variables. Okay. So right now we actually extend the model into the CGM model into robust procedure. So we assume the p-dimensional random variable y is still continuous with still unimodal and the symmetric marginal distribution. Each of the random variable is following unimodal and something like some distribution with unimodal and symmetric marginal distributions. And we think about the random scale transformation. Actually, the scale we consider to scale these random variables. However, the scale parameter dv is not fixed. It is, we are considering this dv, which is the positive value. It is following some distribution, positive distribution pv. And so the big diagonal matrix D is now includes the diagonal elements, has the 1 divided by di. And then this scale, so each random variable y is scaled by node specific, variable specific scale parameters di. Okay. So after we transform the original variable, when d is known, right? So then the transformed random variable is following normal distribution. That's what we assume, right? So if we know d, and then we just construct the CGM model using the previous methods, we can kind of find the mean parameter b and the k, right? However, even though we found the structure using this model after transforming, we don't know the actual interpretation on the original scale of y. So this is actually the chain graph model for the transformed random variable dy, not for the random variable, original random variable y. So that's why this we wanted to do some theoretical work on interpretation of the resulting the graph structure. So we introduce weaker Markov property here in this work. Okay, so I don't have much time, so maybe I can okay. So first we are using, instead of using just conditional independence, we actually introduce one other concept of the independence. So y1, y2 is sign independent. So this is the new, so if and only if when the probability of the negative of the random variable y1 given the conditioning set Z is kept regardless of y2 in the conditioning set. And also for y2 is the same. So if this equivalence is satisfied, then we say the y1, y2 are conditionally sign independent. Okay, and then as you know, conditional independence is defined by the density, right? So the conditional independence implies conditional sign independent. However, conditional sign independent does not imply conditional independence. So this is the weaker independence property. Okay. So utilizing this definition, we actually find from the RCGM model, the robust model, we wanna interpret the zero structure of the precision parameter and the mean parameter with the conditional sign independence. So n list, if there is if we are considering the edge between u and v, if one of these n list one of the two nodes are non-normal, then the zero structure in the precision matrix is equivalent to the corresponding random variable xu and xv are sign independent given ZU. So here ZU is the AMP conditioning set that I actually introduced at the beginning. Okay. So and when U and V are in different layers, the zero element in B means that the corresponding random variables are sign independent given again the AMP conditioning set. So the edges that the corresponding nodes are both normal are interpreted with the conditional dependencies following the AMP. So if both of the nodes are normal, following normal distribution, then the conditional independence is satisfied here. Okay, so this is our main theorem. And then to see the relations between the the CSI, CI, CD, and CSD, we can see this diagram here. So if there is no edge between the node U and V, we can tell about the CSI depending on if the two nodes are at least one of the nodes are non-normal, then we can tell only CSI. And then if both of the nodes are normal, then it is conditional independent. And also if we find the edges, for the edges in the structure, we can, the edges can be interpreted as conditional sign dependent. If both of the nodes are at least one nodes are non-normal, then it is interpreted as conditional sign dependence, which is stronger property than the conditional dependence. Okay. So what it means is that if we find for the graph structure, if there is edge there, right, then these edges has the conditional sign dependence relations, which is stronger property than the conditional dependence when the nodes are not normal. Okay. However, we didn't want to do it like in deterministic way. We want to binary. We don't want to binary. We don't want to decide if this node is normal or not normal. rather than doing that, we wanted to quantify the non-normality of the nodes in a continuous scale, so like in probabilistic sense. Okay, so that's why we actually use the mixture priors of the for the scale parameters dV here. So when the omega v is the indicator for dV is equal to 1. So when dV is equal to 1, the node is normal, right? We don't need any scale parameter, right? If it's not 1, but positive value, then it's not normal, right? So the dV given omega is following the mixture distribution. When the dV is equal to 1, it is actually following the density PV, and also the omega is 0, and dV is following the direct delta function at 1. Okay, and then omega v again is, we assume that omega v is the Bernoulli trial with the proportion pi v. So instead of making inference on dV or omega v, we are making our parameter of interest is becoming to pi v here. So pi v bigger, we have like close to 1 pi v, then it means the node v is more likely to be non-normal. Okay, so pi v is kind of continuous measure of non-normality for node v. Okay, so
Dr. Ha,
yeah.
Ha, I'm sorry, could you wrap up pretty soon?
So I will
please?
do it.
Yeah.
Yeah.
Thank you.
Thank you. So I actually extended the theorem into corollary when incorporating the continuous measure of pi u and pi v. So if we know GVU, which is the posterior probability of the edge inclusion, and we also know the non-normality of the node pi u and pi v, then we can actually probabilistically interpret if the edge is sign independent or sign independent or just independent. Okay. Yeah, so this is the simulation results. So comparing to other like a Gaussian model-based approach, our approach is getting better when there is more non-normality included. Okay, so this is the application results, and so in summary, so we CGM, the chain graph model, accounts for dependencies in the multi-layer data, and the Bayesian approaches can be used for estimating it. However, for handling the Gaussian robust for handling non-Gaussian data, we actually proposed robust procedure, and also we developed a weaker Markov property on this kind of robust algorithms. Okay, so yeah, so thank you. So this is all for my talk. Okay, thank you.
Thank you, Dr. Ha. We are sorry that we cannot give you more time. So big claps, applause. Okay, so we will move to the next presenter, Dr. Seungyeoun Lee from Hyojung University in South Korea. She is also the president of Women in Statistics in Korea. We call it WISK. That's the Committee for Women in Statistics in Korean society. So she's going to give a brief introduction of women in statistics in Korea and Korean Statistical Society. And at the end, I'll just promote the IBC 2026, and then we'll finish. Okay. Please, Dr. Lee.
Thank you. Thank you for introducing me, Dr. Park. Okay, I'm so glad to organize the WISK session at the International Day for Women in Statistics and Data Science Conference. You already heard 3 speakers' presentation in the previous session. Now, let me give a brief introduction of WISK. This is the history of WISK in the last 5 years. Okay, in 2019, Professor Taerim Lee of Korea National Open University established WISK together with several professors who share the same thoughts. After joining the group support program of the Korea Statistical Society, Korea Foundation of Women's Science and Technology Association, we have been hosting academic sessions in the Korean Statistical Society and holding academic and job seminars for students. And today, some of our WISK members are giving speeches here at the IDWSDS conference. Okay, let me talk about some activities of WISK in details in the next slides. This is the, actually, we have, we have 10 voting members. Let me see. 10 voting members shown in this list. Okay, they are all professors of universities and belongs to Department of Statistics or Biostatistics. And Hyojung Lee continues to help as an advisor. Okay, this is the main function of WISK. First, we have been hosting regular academic session in Korean Statistical Society conference. And second, we have been holding academic and job seminar for students. Third, we are forging links with the Korean women statisticians. And finally, we are constructing global networks women statistics. This is the activity risk of this pic. Okay, you can see. Anyway, I really appreciate, let me see. Sorry, I really, as you see in 2023, I really appreciate Dr. Dongyeon Kim for participating in the regular academic session in Korean Statistical Society conference in 2023. She gave us introducing KSS women in statistics and data science. Okay. This is a picture. These pictures of the academic sessions. As you can see, is that this is Dongyeon Kim's presentation. Okay. This is another WISK activities for academic and job seminar for students in statistics. Okay. Now, this is this is pictures. This year we had a job seminar for students in September 22nd. We invited two famous women CEOs from South Korea and the LG Plus company. They gave an excellent talk to students about their experience in the industrial field. There are many Q&A from students on how to prepare for getting a job in AI and data science field. So we had a very great time with many students as shown in the picture. In addition, we had one session for discussing about gender unconscious bias. Also, we had WISK also supports mentoring programs for students. It helps to build networks between women statisticians and the students. Also, it provides support to the students who plan to pursue a job or a career in statistics. The program was conducted online and small groups. This is picture. This is pictures for mentoring program in 2019 through 2022. These pictures are activities for forging links with Korean women statisticians. In this meeting, students were able to meet women executives from various fields of statistics. Okay. Also, in 2019, the Professor Lee attended the Korea Japan, US Forum, and Women in Statistics as a panel. Last year, we participated in the KSS for Women in Statistics luncheon at the 31st International Biometric Society Conference in Latvia. Professor Hyojung Lee joined the panel discussion, and Sohee Park also participated in this luncheon, as shown in the picture. Since IBC 2026 will be held in Seoul in Korea, Sohee Park, who charged a co-chair of IBC 2026, will advertise IBC 2026 more after my talk. Okay, now let me introduce very briefly the Korean Statistical Society. The Korean Statistical Society was established in 1971 for the purpose of the development of statistics and research in related fields. The KSS has the two conferences twice a year, May and November by 2021, but it changed their schedule to June and December after 2022. Also the KSS has published three journals. The first one is a journal of the Korean Statistical Society, and second one is the Korean Journal of Applied Statistics, and third one is Communication for Statistical Applications and Method. Also, KSS has 10 sections according to the research field. Here is official statistics, industrial statistics, Bayesian statistics, classification, biostatistics, survey statistics, statistical computing, statistical education and consulting, statistics in finance and insurance, and statistics in sporting. Also, the KSS some global activities. The 53rd International Statistical Institute World Statistical Congress has held in 2001 in Seoul, and again in 2027, the 66th ISI World Statistical Congress will be held in Seoul, in Busan, in Korea. It held the first IMS Asia Pacific Rim meeting in 2009. And finally, we will hold the 33rd International Biometric Conference in 2026. Okay, thank you for your attention. Dr. Park, your turn. Okay.
Yes, I'll just briefly talk about the IBC 2020. So let me just briefly share. Okay, so can you see my slide?
Yeah.
Yes, so as Dr. Lee mentioned, we're going to have this International Biometric Conference in Korea in 2026. So in 2022, it was held in Latvia, and then 2024, it was going to be held in Argentina, but because of those circumstances in that country, it was recently decided that it was going to be held in Atlanta in the USA. And then since this is every 2 years, we will hold this conference in 2026. So I just want to make sure that all the participants here, you will be interested in coming to Korea. This will be a very good opportunity, not only for the academic networking, but also it will be a good excuse for you to come to Korea and have some cultural experiences for K-pop and K-drama and K-food and everything. So I'll be the co-chair of this IBS local organizing committee, and Dr. Ho Kim at Seoul National University, he'll be the co-chair. And we have these local organizing committee members, which is also expanding right at this moment. And this will be organized by the Korean Biostatistical Society, and this is also the Korean region for International Biometric Society, and I'm currently the president of that society. So this is just the promoting for you to come to Korea, why it would be interesting to see. It's easy and convenient access, and it's safe and secured, and it has outstanding infrastructure, unforgettable cultural experiences. And, you know, the Korea has an excellent subway map here. So it looks complicated, but you can pretty much go anywhere with very cheap rate. And you can have a no visa policy from over 100 countries. And with the cultural experiences, we also have old and new harmony in Seoul, Korea. And you can experience a lot of variety of Korean food, which is also healthy. So I hope you will be able to plan in advance to come to Korea for this IBC 2026. Okay, since our session is time is up, so we're going to finish here. And thank you everybody for participating in this session, and all the speakers, and Dr. Dong-Yeon Kim again for being here at your late time in the United States. So we'll finish here. Thank you very much, everyone.
Thank you.